So I'm going to quickly walk you through the analysis for the RC circuit. So what you should have on your worksheet is the circuit resistance and the circuit capacitance, and you should calculate the theoretical time constant tau, which is just the R times C, and it gives you the time constant in seconds. Then you're going to have collected some data on the second side of this page. So I'm going to scroll down, and you see there's your data. You've got your time. You're going to write down what your current values are, and the third column is for the natural log of the current. But remember, we're going to throw this into Excel, and computers are great at doing calculations for you quickly, so you don't need to do that in your calculator. So you'll have taken data every 5 seconds up until 90 seconds, and then you'll continue every 10 seconds until you get to 360 seconds. Okay, so let's go to the spreadsheet. So the spreadsheet, here I've already copied over some values for current in milliamps as a function of time. So I put in all my values, and the spreadsheet should automatically give you your graph 1. So if we go back to the worksheet, under analysis, it tells us we need to make two graphs. Graph 1 is a plot of the current versus time for the charging circuit, and graph 2 is a plot of the natural log of the current as a function of time. So let's go back, and we've got our first one already made. The axes are already labeled. Now we need to do the natural log of the current. So in column C, we're going to click in that top cell, and we're going to go in and we're going to type equals natural log, which is ln, open brackets, and we want to do the natural log of the value that's in cell B3. So type that in, hit enter. Now click on that cell and copy that equation down. So again, remember, hover over the cell, go to the corner until your cursor turns to a black plus mark, and drag that down. And it calculates the natural log. And now you can see that your second graph is already made. And your second graph has a trend line on it. That's a nice straight line. These data here look very perfect because I manufactured them. Your data might have a bit of scatter in it. Okay, so that's all the graphs done. Now we just need to do the analysis. All right, so we're going to do the analysis to get the time constant off of each of the two graphs. So from the top graph, what we're going to do is we're going to look at the current at a certain time, and we're going to record the current and that time in the green cells in the boxes over on the right side of that graph. So usually what I do is I say pick the one at 10 seconds. So we're going to say time t1 is 10 seconds. So I'm going to put that in, time 1 is 10 seconds. And the current at time t1 is 25.72. The reason I don't use the value at 0 seconds is you'll see when you take the data that the multimeter takes a little bit of time to respond, so at 0 seconds it hasn't quite come up to the maximum value of current. Alright, so now what we need to do is, now you see in this cell down here underneath it says predicted current at time t2, which is current 1 divided by E, or 0.368 times current 1, so it already did that for you. So it says now you want to look at your graph and find at what time is the current equal to 9.462. Right, so I'm going to go to my current. I'm going to go down and say when is my current equal to 9.46? And here it's exactly at 75 seconds, so I'll put in 75 seconds. For you it might be somewhere in between two times. So in that case you have to interpolate and say, maybe it's 102.5 or 81.3. So interpolate a little bit. So I say mine is exactly at 75 seconds. And then you'll see down here in this red section, it will tell you what your time constant is. So your experimental time constant is 65 seconds. Okay. And that is what I had put my calculation to be. So that's the correct number. So if we go back to the worksheet, you'll see the worksheet has slots for this same things that are on the table. So it wants I1, that was my 25.72. My T1 was time 1 was at 10 seconds. I2, let me put it side by side. Let's see, it doesn't want to do it. I2, drag that over if I can. So I2 is 9.46 and T2 was 75. So that's what I'm going to put in here. You're going to have different values, of course, for your circuit because you have a different R and a different C value. So the experimental time constant is calculated here, and then you'll calculate the percent difference between what you got from the product of your R and C values up the top and what the experimental value is in this box. All right, then the next thing we're going to do is we're going to look at the second graph. So the second graph should be a straight line, and the slope of that straight line should be -1 over the time constant. So we need to find the slope and then use the slope to calculate the experimental time constant. So let me make this big again so we can fit it all on. And we'll go over to that graph. So we see, first of all, yes, it is a straight line and it has a negative slope, so that's great. And this equation here tells me what my slope is. My slope is minus 0.0154. And so the time constant, R times C, is just going to be -1 over the slope. And I have the equation in there already for you. So as soon as I hit enter, it's going to tell me what is my experimental time constant. It's going to be 64.93 seconds. So very similar to the 65 seconds that I had there. Okay, so that's all the analysis you have to do. You go back, you put that onto your worksheet. So the charging slope was minus 0.0154. The time constant is -1 over the slope. And then again do the percent difference between the theoretical and your experimental. And that's it. That's all you have to do for the analysis.